Okay. Cool. All right. A couple of housekeeping notes. The Unit 7 assignment is due on Friday. The Unit 8 assignment is due a week from today, I think. We pushed those back since it took us a little bit longer to get through some of that material. Yeah, I think that's it. As far as administrator, so I sent out an email that you have like a sort of tentative calendar of how we're going to get through Chapter 9. Chapter 9, after reading it, might end up being my favorite chapter in the entire book. Which should scare you, right? But I think it's awesome. So I'm very excited to get through that stuff. So let's see. Yeah. So this class has, I've learned, this sort of reputation for, there's a point in the semester where the difficulty like ratchets up pretty intensely. I think today is that day. So, and the reason for that is we're going to transition here, right? So up until this point, we've basically just warming up, right? We've just been learning the tools that we need to know in order to do the things that we want to do. And today we're actually going to start doing. So that makes things a little more abstract. If you maybe, weren't very diligent about reading up to this point, you might struggle with some concepts because now you got to really know what we talked about in the past. Because now we're going to apply it to some new stuff, to some actual applications stuff. We're going to start talking about things that will ring bells and sound familiar to you from your computer science classes and stuff like that. We're getting to the real meat of digital design. But that being said, don't be scared. I think it's going to be fun. But first, actually, we're going to take a minor detour back to Chapter 7 real quick. Because there was a couple questions at the end of that assignment that I realized that we just totally skipped over. We didn't even talk about in class. But thankfully, it's actually quite easy. So the first thing we're going to hit today is called gate conversion. Using alternate gate symbols. Gate symbols. We also start thinking of this as lazy gate conversions, right? Remember at the end of the day, we built our logic circuits. We want to convert them to circuits of Nand or NOR gates, right, in order to make them more efficient, faster. And so we have processes to do that. But here we kind of suggest a sort of lazy approach. So first, remember our friend, the buffer. The buffer takes X as input, and the buffer doesn't do anything. The buffer gives X as an output, right? Minus some time delay and some power stuff that's kind of outside of the scope of our discussion today. We sort of assume that it does nothing. But if we take the buffer and we add what we call a bubble on the end of it, now it becomes an inverter. X goes in, goes through the buffer, hits the bubble, and X prime comes out. Now, as it turns out, we can put the bubble wherever we want. There are some traditional places to put it, but let's see, this is the bubble, and it can go anywhere, right? The bubble is attached to the outside of the logic gate. Whatever happens in the logic gate happens, and then it hits the bubble on the output, that gets inverted. But we can also put it on the input side. So for example, we could do this. It's kind of weird looking, but it's totally valid. Right, here we have the X on the input. It hits the bubble. There it's going to become X prime. Passes through the buffer so nothing happens to it. And the resulting output is X prime. Functionally, we've done the exact same thing. In both cases, we have an inverter. One, we just draw it in the traditional way. The other, we draw it in a way that you'll see from time to time. They exist. So here's what we mean by alternate gate symbols. Both of these are inverters. One is sort of the traditional one, and one we think of as the alternate. And this applies to AND gates and OR gates as well. So for example, let's take a look at an OR gate. Do you have a question there?
No, it's like a film test.
Oh, all right. All right, so the regular OR gate. We got A, we got B, we got an output A or B, right? But we had a bubble to the output. Well, now we have still A or B, but it passes through the bubble, and we have A or B prime. A NOR gate, right? We could also just apply a bubble to maybe just one of the inputs and get A and B on the input. And on the outside, we'd have what?
A not or B.
We'd have A prime or B. What if we did bubbles on both inputs? So we've got a bubble on both inputs A and B. That's going to get us what? A prime or B prime. What's special about A prime or B prime? So set off a little red flag in your mind.
It equals A and B.
Not just, not quite. It's close. So A or B prime is equal to
A B prime.
A and B prime. And what kind of gate is that? It's a NAND gate. And thus we've arrived at our sort of punchline here. If we want to create a NAND gate out of a NOR gate, in addition to swapping out the gate entirely, we just add bubbles on the inputs of the OR gate, and then we effectively have a NAND gate. Does that make sense? Same thing works for AND gates. We'll skip straight to the end here. We have A and B, and then we put bubbles on the inputs. Well, then we're going to have A prime and B prime. And we remember from De Morgan's theorem that A prime and B prime is equal to A or B prime. Which is an OR gate. So you can put the bubbles wherever you want to achieve whatever sort of specific logic outcome you were looking for. In here. It also kind of simplifies our transition, right? So if we start with a circuit of AND gates and OR gates, and say we want to convert to NAND gates, let's do this. Let's say we start with an OR gate. Now to that A prime and B. That feeds to a level of AND gates, which has what here? C and B and E. And that feeds into another OR gate that has that guy, and let's call it F prime. And output Z. So here's a 3-level circuit of AND gates and OR gates. And we can say, let's convert it now to a circuit of NAND gates. So it's already set up with that OR gate on the output, so all the same rules apply. The only thing we're doing now is sort of simplifying the conversion process. instead of redrawing the entire circuit, all we have to do is add bubbles, right? So, since this is an OR gate, we want to convert it to a NAND gate. We just add our bubbles there on the input. How do we convert these AND gates into NAND gates?
Wait, for the first one, will we do double bubble for like erase one of those for F prime?
I was going to get back around to it, yeah. But you're absolutely right. Since this is a level 1, right, F becomes, or F prime becomes F. Now I've got the AND gates. Yeah, right, it's even easier. You put your bubbles on the output. Now for this last one, A prime and B, yeah, bubbles to make an AND gate, and then of course since it's level 3, you gotta flip it over. That's all there's to it. Yeah.
Just to clarify, we would only do this like this if we explicitly told to in the instructions, right? Otherwise we would.
You do that thing again where you ask me like about an assignment? Yes. Follow the instructions specifically. If I want you to do it that way, I'll ask you to do it in the assignment. Such a buzzkill, man.
Feels like a reasonable
So
question.
if we have to flip, like F, if we have to flip that to regular F, and then we just invert it again, could we just leave that bubble off since
You
it
bet.
doesn't make anything?
Yeah, exactly. So this will be the final point, right? Since these things get inverted, right, we have F prime here, we have what, A prime and B, right, to achieve the same effect, right, we could have just like left this bubble off, since inversion is inversion, right? And we could have left those bubbles off. Now, some might argue that
They're not NAND gates?
they're not AND gates, or they're not NAND gates, right? Which is true. So, but in your sort of drawing, you can get away with it. You're still going to have the same effect in either way. But yeah, but the circuit specifically asks you, or the spec specifically asks you to make NAND gates with bubbles, then you got to do it that way. That person can make the argument, well, those aren't technically NAND gates either. Those are OR gates with inverters. More stuff on top of it, but no worries. Yes. And yes, on an assignment test, I'll specifically tell you which one I want. All right. Any other questions about that? All right. That's chapter 7. Let's put it away. Now, where are we at? Today, we're going to talk about a handy piece of hardware that we use all the time for a bunch of different things. It's called a multiplexer. Or just a MUX for short. From your computer science, your programming classes, hopefully you're familiar with this construct. If something, then something, or else something, right? If else block. A multiplexer basically is just a hardware implementation of an if else block. We'll say something like, if we have 2 inputs, just call them like I0 and I1, one output, Y, and we want to select between these two. We're going to need to add another type of input. We're going to call it a control input. We'll call it C. And we'll say if C equals 0, then Y equals input 0. Else, or another way to say that, maybe a little more formally, since there's just two cases here, right? If C equals 1, then Y equals input 1. So if C equals 0, then we'll set Y equal to whatever I0 was. C equals 1, then Y is set to whatever Y1 is. And then of course we could have a much longer statement than that depending on the number of bits. Now mechanically, we're going to model this as a switch. So we got I0, we got I1. Let's put the switch in the normal position of pointing at I0, right? Since the case when we're not applying the signal. Think back to our first discussion of logic gates, right? If no signal applied, if the variable is equal to 0, the switch stays in its normal position. Otherwise, it clicks over to its other position. And whenever I put Y, and we use the Boolean variable C to indicate the switch, right? So if C is equal to 0, then no power is applied to the switch, and it will stay in its position connected to I sub 0, right? And I sub 0 will feed out to Y. If we apply a signal to C, if set C equal to 1, then the switch clicks over to I sub 1, and then I sub 1 is fed to Y. Now how can we express that as a Boolean expression? Because again, at the end of the day, we've got to make it out of logic gates. So first off, we know this Y equals something, right? So Y is equal to I sub 0 when C is equal to 0. It's equal to I sub 1 when C is equal to 1. So we could write it as...
Would it be C and I naught or C and I1?
Let's write that down. C and I naught or C and I1. It's not quite that. What are we missing?
C naught I instead of C naught I1 instead of C naught I.
C naught I1? For sure. What do you guys think?
Maybe C naught I0.
What's that?
C naught I0.
Yeah, C prime and I0, right? When C is equal to 0, then Y is equal to I sub 0. So it's got to be I0 times, not times, excuse me, and C prime, right? So that if C is equal to 0, then Y is equal to I0 and 1, or I1 and 0, right? Which simplifies. Anything and 1 is going to be itself, so Y is equal to I0. And likewise, if C is equal to 1, then Y is equal to I0 and 0, or I1 and 1. Y is equal to I1. All those zeros and primes trip you up. Now that's the gist. That's the structure of multiplexer. Are there any questions about that? So then from there, it's pretty relatively easy to build. I'll draw the logic circuit for because it even nicely comes all the way, or already in that nice sum of products form. So we have what? I0 and C prime 1 and C, just like that. And then the output is Y. Now we refer to this as what's called a 2-to-1 mux. Because it takes 2 inputs and condenses it down to 1. So you get all kinds of sizes of multiplexers. You have 3-to-1, 4-to-1, 5-to-1, 64-to-1, 128-to-1, right? All kinds of bits and pieces. Yeah. And we traditionally draw a mux, because we don't ever draw this, and since we have a structure for it, we draw a mux looking like this. We're going to draw a trapezoid. Coming down the left-hand side, we'll have all of the inputs. I sub 0, I sub 1, Y on the output, and then coming down from the bottom, we'll have our control. So this is, a logic circuit symbol for a mux. Any questions about that? All right, so let's go ahead and make a bigger mux. Let's make a 4-to-1. See what that looks like. So if I have 4 inputs now, I'll just label I0, I sub 1, I sub 2, and I sub 3. Here we're building a 4-to-1 mux. My next question is, well, how many control bits will I need in order to make all my selections?
2.
What's that?
2.
Yeah, you gotta have 2 bits. Right? If you want to select between one or the other, then you gotta have 2. So we'll have a C1 and a C0. Let's see, what is that going to look like? I don't want to write this. So Y is equal to, now since we have 2 bits of control to select each one, it sort of makes our expression a little bit larger, right? So if we say I0, so Y is equal to I0, and we have to step through all of the possibilities for C, right? I0 and C1 prime and C0 prime. Or I1 and C1 prime and C0, not primed. Or, put it down here, I2 and C1 and C0 prime. Or I3 and C1 and C0. Any questions about this expression? So again, we would just have Nand Gates. We have the first one, I0, C1 prime, C0 prime. Second Nand Gate would have I1 and C1 prime and C0. The third one would have I2 and C1 and C0 prime. The third one would have I3 and C1 and C0. And they all feed into a 4-input OR gate. And we'd have our output Y. We went farther. What if we had an 8-to-1 multiplexer? Now how many bits of control?
3.
Good, 3. A to 1 mux. Let's see, that's going to have what? Y equals I sub 0 and C2 prime, C1 prime, C0 prime, I sub 1 and C2 prime and C1 prime and C0, or I sub 2, C2 prime, C1, C0 prime, or I sub 3, C2 prime, C1, C0, or I sub 4, C2, C1 prime, C0 prime, or I sub 5, C2, C1 prime, C0, or I sub 6, yeah, and C2, and C1 and C0 prime, or I sub 7, C2, C1, C0. The pattern just extends out forever, right? So, two things to notice here. One, this can get out of hand pretty fast, right? Doesn't take us very far before these logic expressions get kind of crazy, and the logic diagrams become no longer sort of worthwhile to draw. And even the sort of basic schematic that we have gets a little unwieldy, right? Or the symbol that we have. So if we want to draw this just in its condensed form, right, just in its trapezoidal form, right, then I need 3 lines for C2, C1, and C0. Then 1, 2, 3, 4, 5, 6, 7, 8. I0, I1, I2, I3, I4, I5, I6, and I7, and just one output block. So what we're going to do now is we're going to introduce a concept called bus notation to make this just a little bit more condensed, a little bit easier to write. Bus notation. So what we're going to do is we're going to take this so draw the trapezoid, and I'm going to draw one line and just call it I, and I'm going to make a dash through it, and underneath I'm going to write an 8. So it's possible we've heard that concept of a bus before in this sort of context, and a bus just is a bunch of signals all sort of crammed together on one sort of bank of lines.
Like a USB?
Exactly, yeah. Yeah, USB stands for what? It's Universal Serial Bus, right? Bunch of signals all on one cable. And then I can draw my control now as just C with a dash 3. And our Y output is still just 1 bit, right? So no dash. It's not a bus. It's just one line. So here we say that I, the notation we're going to use if we want to write out what's in the bus is going to be like this. Yeah. We'll do what? I sub 7, comma, I sub 6, I sub 5, I sub 4, I sub 3, I sub 2, 1, comma, I sub 0, right? So basically put all the signals in the curly braces put them under one symbol. And by convention, although it's not always required, and there will be cases when you don't do it this way, typically your bus is the Boolean variable for the thing, right? And then everything inside the bus is like that with subscripting. You guys worked with arrays yet in your CS classes? Yeah? Working with buses is going to be very similar to working with arrays. All right. That's bus notation. So to generalize everything, because we don't have some rules, I have to redesign it every time. I'm going to end with a model for what we're going to call it generalized. 2 to the n to 1 mux. By convention, you're not going to make a 3 to 1 or a 6 to 1 or a 7 to 1 or anything like that. You're going to try to keep them in powers of 2. We would say that the expression, or so we would draw it with a plus, input I, that value is 2 to the n. You got an output y, and then you're going to have n control the bus size n. So you have 2 to the n inputs in the control bits and 1 output bit y. You generalize by saying that y is equal to the sum of, I'm going to say k equals 0, just have another variable there, 0 to 2 to the n minus 1 of the minterm of k, and that's going to come from our control bits, and I sub k. So n is the minterms of c. And that's a sort of basic fundamental model. Any questions about that? You don't need to use that particular thing a lot. All right, one last thing we're going to talk about is, well, how would we sort of create a multiplexer that's composed of smaller multiplexers, right? We don't always want to create these big, sort of monstrously long banks of AND gates, right? We want to sort of modularize things. Instead, build larger multiplexers out of smaller multiplexers. When we talk about hardware description language, this will become really important, right? It's a lot easier just to create a small module, use it 3 or 4 times, and then constantly go through the whole process of making your K-maps and creating your logic circuits every single time. So what I want to do here is say, compose a 4 to 1 mux out of 2 to 1 muxes. So to do that, let's start with the Boolean expression that we've already drawn or written out somewhere for the 4 to 1 mux. So remember that has I0 and C0 prime and C1 prime. I'll flip those around. Do C1 and C0, or S1, C1 prime and C0, 4, I sub 2, C1 and C0 prime, or I sub 3, C1 and C0. So we've got to change this into a circuit that consists of 2 to 1 multiplexers, but we've got to adhere to all the same rules that we've had before. We're going to do it with Boolean algebra. And it turns out it's relatively easy to do because we can factor out some things. So notice that in these first two, the term that they have in common is C1 prime, C1 prime. Now the second one, it's got C1 and C1. So that means that if C1 is equal to 0, then we know that we're going to be selecting from this first half of the circuit. And if C1 is equal to 1, we know we're going to be selecting from the second half of the circuit. So algebraically, what we can do now is we can factor out the C1 terms in either case and say that y is equal to C1 prime and I0 and C0 prime, or I1 and C0, or C1 now and I2 and C0 prime, or I3 and C0. So hopefully now you can see we have a sort of larger multiplexing structure, right? C1 prime gets us this, and C1 gets us this, and inside we have a multiplexer again, right? So I0 with C0 prime and I1 with C0. So let's go ahead and draw it. Let's see. Okay, so the first thing we're going to have is this beginning level, right? We're going to have two concurrent 2-to-1 multiplexers. And an OR gate. And this first one we'll take from I0 and C0 prime. Second one we'll take from I1 and C0. That's our first mux. Then we have our second 2-1 mux. And this time we're going to pull from I2 and C0 prime and I3 connected to C0. And that's our second 2-to-1 mux. And then the outputs of these two logic circuits, oh no, will be the input to our second 2-to-1 mux. So that first one will come with, what was it, C1 prime. And that second one will come with just C1. And there's our output, Y. And there's our third 2-to-1 mux. So in this case, let's see, 2-to-1 mux. We were able to build a big 4-to-1 mux with just 2-to-1 muxes.
school we ever want to draw a system like that using the trapezoid stuff? Or do we always want to build it modularly with little logic gates?
So that's a good question. That was a fantastic question.
The same as all of my questions.
No, it's not the same as all of your questions. Or maybe it is, but you worded it in a way that would feel good. Yeah, so you could totally turn around and draw this like this, right?
Is it like how with AND gates you can have like A and B and C and have like a bunch of gates, or you can combine them into one big gate?
Exactly, yeah. So we'd have I0 and I1, and I2, and I3. Both of these muxes take C0 as their control bits, and then our output Y. But then, of course, at the end of the day, you really just do it like this, right? Have Y in the outputs. You have a 2-bit bus for control, and a 4-bit bus for your input. All right. So with our last, 6 minutes, what if we wanted to convert this to a circuit of Nand gates or NOR gates? First off, what can we do? Nand gates or NOR gates?
NAND.
What's that?
NAND gate.
Say one more time, sorry.
NAND.
Yeah, Nand gates. And why Nand gates?
The ends with NOR.
Because it ends with an OR, right? Now we're going to get a structure that basically looks exactly the same, except not except anything, right? It would work if we treated each of these individually, and it would also work if we treated it as one 4-level circuit, right? Because no odd level, so this is level 1, and that's level 2, and level 3, and level 4. And you can see if we built it out even farther, because of the way it's structured, no odd level is going to have any individual inputs, right? So no random single literals are going to get inverted. So just to say we did, now we have NAND gate, NAND gate, NAND gate, NAND gate, NAND gates all day. That's Y. Just 1. I0, I1, I2, I3, C0 prime, C0, C0 prime, and C0. So here, isn't that beautiful? Look at that. 4-to-1 multiplexer composed entirely out of Nand gates. Oh, I lied. There's one more thing we got to talk about. Oh, we shouldn't have spent the time on the Nand gates. So all of these, so it's a 2-to-1, it's a 4-to-1, it's an 8-to-1, it's a 64-to-1. But how many bits are they? Right, these are all, as big as this guy is, it's a 4-to-1 multiplexer, but the individual input signals that we're trying to select are themselves just 1 bit. So how do we create what's called a, well, I don't have a name, but how do we create a multiplexer that had 4 bits, or 8 bits, or 64 bits? So if I wanted to say, make a, we'll call it quad, or 4 bits, 2-to-1 mux. How can I do it? Right, the signals themselves have to be 4 bits, but the muxes themselves are 2-to-1. Punchline is, you got to use 1 mux for each bit. So let's say that we've got inputs A and B, which themselves are 4 bits, A3, A2, A1, and A0, and B is what? B3, B2, B1, and B0. And we're going to output Y, but in this case, Y also has to be 4 bits, right? So Y is composed of Y3, Y2, Y1, and Y0. How many control bits do we need?
4.
Not 4. Still just 2, right? Because we're still selecting between 2 entities, right? 2 individual things. So even though we're going to break it out into 4 pieces, to do each 4 bit individually, the control bits are still the same. Still just the, actually back, not 2 bits, just 1 bit. So what we do is we stack, let's see, do it this way, yeah. 1, 2, 3, 4. We stacked up a bank of multiplexers, and that's going to get us Y3, Y2, Y1, and Y0. The first one takes A3 and B3. And the second one takes A2 and B2. Where have we seen a structure similar to this already?
Addition.
Yeah, when we built those adding circuits. We already did something a lot like this, right? So here's the basic setup, but each mux is going to be driven by 1 C, right? Because you don't want to select, A3 and A2, but also B1 and B0, right? You want all of A to get passed through, or all of B to get passed through. And so all of those guys are going to be tapped to the same control bits. This is why we make the distinction between logic inputs and control inputs. So that's it. All right. So, any questions? That's multiplexers. Yes, sir.
For example, you said there's 2 bits for C, so C should be a bonus with 2 bits, right?
I misspoke. I meant the control should be 1 bit, since we're selecting 2 entities. Now, if we were making a 4-bit, or let's say this, if we're making an 8-bit 4-to-1 mux, we would need 8 multiplexers, each with 2 bits of control, right? Cool. All right. Yeah, that was kind of sad.
In practice, would they use actually 4 hardware, or would they just use 1 but just reuse it? Like 1 clock cycle, they'd use like the index 3, the next clock cycle, they'd use index 2, index 1, index 0, etc.
Well, it's all hardware. So he asked, we're not quite done yet, both girls. He asked a great question, which is, would you, in practice, would you do it with multiple multiplexers, or would you like index through them? And the answer to that question is, well, you have to use multiple multiplexers because we're doing it in hardware. Right? We're not doing it in software. We don't have the advantage of, we can't index anything, right? Because it all has to physically exist, right? So in software, in code, in Python or in C++ or whatever, yeah, you can build an array and you would index it through that. But that's because that is built upon these structures that already exist inside the processor. We, in this class, have to physically build them ourselves. So, all right, I'll see you guys on Friday. Thank you.
Are we going to be building a basic type of CPU in class at some point?
We're going to build bits and pieces of them, but I don't think we're ever going to put them together in one solid piece. But maybe,
Okay.
I don't know. There's another class for that. All right, kill those.